Our project is inspired by cephalopods, such as octopuses, cuttlefish, and squid, because they show surprisingly complex cognitive abilities despite having brain structures that are very different from vertebrates. They are capable of rapid learning, memory retention, problem solving, and flexible behaviors that make them valuable models for robotics. In this project, we built the Octobot, a bio-inspired soft robot designed to classify objects through touch using a single embedded pressure sensor. We also investigated how a cuttlefish-inspired autonomous agent learns to make decisions between immediate and delayed rewards.
So for the robot itself, it has a off-the-shelf Lego Spike Prime base with an ESP32 microcontroller. It has several flexible tentacles that have a pressure sensor embedded in it. It has a custom 3D printed shell with an LED matrix that allows it to camouflage. And then there are 9 objects that we're using to test its tactile sensing abilities with various textures, densities, and sizes. So for the data collection, when the servo spins, it pulls on this fishing line that's strung throughout the tentacle, which actually curls the tentacle and allows it to grab an object, producing this pressure time series that you can see in these images. If you look at the top left, you can kind of already see how it splits up into 3 groups, which are actually all sorted by texture. We ran this raw data through a couple of models, and they kind of matched that first visual inspection where it does clearly sort them into 3 models, which happen to all be based off of texture. So then we made a model using random forest, and with all 9 objects, it was accurate about a third of the time. But if we grouped them by those groupings that we saw earlier, that accuracy improves to 95%. And then finally, we integrated this model onto the robot, and it actually gives you live input on what object it thinks it's sensing. So it's able to curl, grab the object, and then flash the shell with what object it's grabbing.
In the delay gratification test setup, the agent chooses between left and right. In experimental trial, one side has a live stream and the other side has a dead stream, so the agent must choose between a higher value delay reward and a lower value immediate reward. In control trial, one option is unobtainable and the other is dead stream, so waiting does not give the same benefit. The reward values are live shrimp equals to 5, dead shrimp equals to 1, unobtainable shrimp equals to 0.5. For the simulation, we use a Q-learning agent. The agent learns reward values for each state action pair, then use softmax action selection to choose left or right. We also added a patience function, which discounts only the live stream option as delay increases. The graph shows that the agent learned the correct reward preference during training. Then, as delay increase, experimental performance drop, while the control conditions stay relatively stable. For the physical implementation, we transferred this model onto a turtlebot. The robot used ROS2 navigation and camera-based color detection. Yellow represents live stream, red represents dead stream, and purple represents the sliding door marker blocking the delay reward. The robot detects the marker, chooses the chamber using the Q table, waits if it selects the delay reward, and then navigates to the chosen chamber to receive reward feedback and update its Q table.
To create a realistic testing environment for the delayed gratification task, we designed an arena inspired by the natural marine habitat of cuttlefish. At the center are 2 wooden chambers with transparent acrylic doors, which prevent the robot from immediately accessing the prey. These doors are color-coded to indicate the type of prey inside, while the rest of the environment avoids those prey colors to reduce visual confusion. Surrounding the chambers, we constructed a coral reef environment with seagrass beds, rocks, and coral structures to mimic the textures and forms found in a real underwater setting. Overall, this project gave us a stronger understanding of how biomimetic robots can be designed, built, and tested to model intelligent behavior. We also learned the importance of communication across an interdisciplinary research team. Moving forward, future work would focus on improving the robot's hardware, including a custom base and additional sensors that could detect properties like size and density. We also hope to combine the delayed gratification model directly into the Octobot,